So 3D scanning systems, these are the two types that we're going to talk about today primarily. And I'd like to open things up by starting with a poll question, just so I kind of have a feel for our audience and what people's experience levels are with 3D scanning. So if you would just take a minute and answer this question. So we've got a little bit of a mixed bag. It looks like a couple of you have. Looks like most people have not. So that's good. That's kind of why we're here. So might be a review for some of you, but anyway, back to the two types, laser line, structured light. So laser line scanning is really optimal for clear parts and hard to see parts. So, things that won't reflect back to the scanner for a surface capture are difficult sometimes with the other type of structured light scanning, and laser can get around that. And where you might see deficits in speed because of just a single laser point, there are now arrays of laser points to speed up the actual scanning process. So whether it's a 5x5 or 7x7 grid, that's increased greatly to the throughput of the scanning device. It does have really nice accuracy and resolution. Typically, metrology uses these a lot. But they don't, most of them at least, don't capture the surface color that the structured light does. And just a note quickly, we're not going to talk a lot about metrology today, so I'm sorry to disappoint anybody that was interested in that. I'll touch on it a bit, but we're primarily looking at the other applications for 3D scanning. So play this quick video of kind of what that looks like. So this gentleman's using a turntable. You can just pivot around the part as well, depending on the access you have to the part and its geometry, how complex it is. So you can see as he's kind of painting along that part, the blue mesh that it's creating in real time. You're able to see that as an operator. You're able to see what's being captured and what areas you may need to go back and redo. You don't have to start over. It's just a matter of covering it again, and the software is intelligent enough that it will build upon any gaps that were there initially. So as you can see, it can be very quick, this step of it. This is not sped up. This is a real-time application. So in a matter of minutes, you can do a fairly large part. And here's another demo. This one doesn't have any sound, but see, it's got another laser with a little bit of a different setup, but it's on a robot arm. So for larger, vehicles, aircraft, larger pieces, again, very fast. So you can see how quickly that green mesh is being populated based on kind of the painting that he's conducting with the scanner. He's relatively close to that. It's anywhere from a few inches away to, it's definitely under a foot, the proximity between the end of the scanner to the object. But you can see the detail and the speed at which you can capture this door on the car. Different setups. We've got basically a robot arm with a scanner, and then we've got a handheld scanner. This is set up again. This can be somewhat automated. You can set up a turntable to spin incrementally and walk away, and the image can be, the object can be captured that way. So this is structured light, blue or white light typically, and it captures the reflection across a whole region instead of just a single smaller point or small area, small window. So the throughput can be much higher. The accuracy is traded off a little bit. So usually metrology is not the best fit for these types of scanners, but the technology is always improving. I can remember when these first came out, and the speed has just gotten dramatically faster. Just think of your computer and speed. It's kind of taken a similar trajectory. So the black reflective surfaces can be a challenge with these. A lot of times we have to apply a temporary powder paint if that can be done to the part. And again, this is just for better reflectivity that the scanner could capture with structured light technology. The other nice feature is you can recognize colors. So some are very, very prolific when it comes to color matching, like a Pantone system. Some of the really high-end scanners can do that, match a particular code or Pantone number to the color. Sometimes you may just want to know, if it's multicolored object, which one is, one of the three colors, for example. But the structured light will give you that opportunity. And this is a quick video of what that looks like, and very similar. This is a turntable setup, relatively small part. And you can see this has got two cameras that are capturing at top left and right on the device right there. So you're seeing on the software screen what the scanner is capturing in real time, and then it's comparing areas in green, red, and yellow that are relative in accuracy to the target part. So this takes a few steps, and we'll talk about that. But basically, towards the end, when you're doing some metrology or comparison, this can be done laying one part over the other, meaning the mesh scan over the actual 3D CAD part that you are inspecting. All right, so what's the workflow look like? So we've got, the first step is to choose the appropriate scanner, whether it's a handheld, whether it's a large format, the type of technology you need based on the accuracy, the resolution required, color, things like that. And then the environment. So, a lot of these have been done in relatively clean area with pretty good lighting. Depending on the environment you're going to be in, you may be limited to a particular type of scanner. If the client can ship you a part versus having to go on site, that may limit as well the type of technology you can bring along. So from there, you're going to collect the scan, and you're going to create the surface mesh. So that is basically the data that is being acquired as you're painting over the object. From there, that mesh, a lot of people think, okay, great, we're done, right? And that's just that's the easy stuff, really. That's kind of the part that takes the least amount of time usually, especially with the technology today, as good as it is. The challenge can be in then repairing that mesh. So depending on how good your scan is and how complex the geometry is when it comes to the number of holes and openings it has, sometimes those all need to be addressed prior to going to a reverse engineering step. So this step, of file manipulation, kind of editing the file is an important part, and there are several steps along the way. But you could, in theory, you could optimize the mesh and repair it and create a file like an STL file or a 3MF file if you're looking for color capture and texture, and send it to something like a 3D printer. And very industry 4.0, new technology that is very nimble, just like the scanner is. So scanning and printing really go together quite well when it comes to the different tasks and time saving that they allow. So this is just an example of how you can go straight from the scan with a little bit of repair and optimization, and with a mesh file, not a solid file yet, but with a surface mesh or a tessellated file, you can send that file directly to the printer and get started on the actual making that part, comparing it to the scanned target item. But for a lot of cases, that's only part of the story, and you're just getting started. Creating the editable solid file is kind of a different animal. And a lot of companies, they won't even do this step. So they would leave it up to a customer or find a third-party service to do this is basically, CAD engineering, basically. It's doing CAD sort of in reverse. Instead of starting from nothing and just sketching out, you're starting with the mesh and fitting the CAD features, whether it's a boss, whether it's a rib, whether it's recognizing chamfers and radii, and that is all part of this step of creating a 3D solid file. There are dumb solids, which are featureless, and there are editable solid files that can be altered and modified for future use. So say you scan a 6-inch part and you want to make it 12 inches. you can do that by identifying the extrusion step and modifying that feature. You can do that with the dumb solid, but it won't be not as clear, and it's not as transparent as to what the changes were. So editable files are different. You can see kind of the timing here, what to expect for some of these steps in the scanning process. So about 30 minutes to an hour is pretty typical for intermediate users, getting you to the point where you have a file that can be sent directly to a 3D printer potentially, something like that, or doing a little bit more work in creating a non-manifold surface file, which can be sent to a CNC machine, for example, and tool paths can be created from. But repairing the mesh, and like I said, it depends on the quality of the scan, whether you did the scanning or someone else did it. It can be a real bottleneck when it comes to this workflow. But the real money is, again, in the CAD modeling. So we're going to talk about kind of the file types a little bit later, as what to ask for. There is a bit of a hierarchy as far as not only cost, but lead time most likely, and then functionality, what each file, what you can do with each. This is just another image of what that looks like. So this is a part that the green basically is the surface mesh. So this has been a surface mesh that we have captured, optimized, and repaired, and basically said this is going to be good enough for what we need to create, which is a 3D solid. And then the blue is the 3D solid, which you're building off of. So you can see how these kind of blend together, which is what you want. You want the solid to match up to the mesh. You want the diameters to match up. You want the outside edges to match up, so that you're creating a one-to-one duplicate essentially, but as a solid instead of a series of surfaces or surface meshes. So this is a step that can take the most time when it comes to feature by feature going through this part. It's definitely the bulk of the project time when it comes to somebody asking for an editable 3D file from a scan. So you can imagine the hours, the engineering rate, the days will add up. So you want to be careful about what you really need and what you're asking for as a client. And then you'll appreciate it once you're doing it later on yourself. How are we going to use this? So looking at manufacturing plant, there's some different areas. Again, these are all outside of metrology or inspection today. So hopefully you guys are well aware of the benefits of using scanning when it comes to either complementing or replacing a CMM type of system, where you are a coordinate measurement system machine that is often used in the quality lab. So again, these are non-metrology inspection related categories. So product customization, you've got a couple of pistol grips here. And so we've got a company using modeling clay to customize the shape of the grip that fits a particular customer's hand. So they've got a clay that will basically compress when the client has their hand on it in a position that they would like to hold the pistol. So the clay then hardens and cures and can be sent back to be scanned, which you see in the middle. You can see that kind of bumpy yellow surface there versus the what looks like to be a parametric-based CAD file that they're marrying the two up. And then, from there, a lot of these are part of a similar endeavor here, where you're non-lethal firearm, but it was a pistol grip nevertheless, and we had covers based on different size pistols and preferences for the client. So from the middle step there, the green could then be split away from the surface of the client's hand profile, and a grip cover could be manufactured in like a molded rubber, for instance, that would have a left and a right and a heel potentially that could be added on to a stock rigid pistol grip. So these are examples of, with firearms, people have some big budgets sometimes for custom firearms and want things to fit just right. And so this is a great example for getting something to fit exactly to that person's hand that they most likely aren't going to find that type of fit right off the shelf. So customization is a good category here. This is an example of a company right here in Indiana that they manufacture of glass bottle molds. So they do a lot of rework and changes sometimes to these blanks and these inserts. So the bottle size maybe doesn't change, but customer to customer, they have an insert and different patterns they want to put in. This is like a basket weave type of a pattern. It's very complex, very artistic. And for this, they were looking at a better way of doing things. It was a really time-consuming, tedious step here to basically trace the tool path of using an end mill that's not cutting, it's just tracing a tool path in 3D and dealing with a lot of complexity when it comes to compound curves and such. So they approached in this case, this is Hexagon. Thank you to Hexagon for this content today. And said, what can we do with scanning? So they found a scanner that they really liked. This is a structured light scanner. And you can see the detail that they can capture in the basket weave pattern there. So instead of sending this to be traced on a CNC mill, they were able to bring it in, scan it in a matter of minutes, and not even do the difficult, sometimes reverse engineering of a 3D solid file, and just live with the surface file to create the tool path, because that's what they really care about is creating a tool path to then do this pattern on other production molds, essentially. So this allowed them to keep their costs down, remain competitive with some other, glass bottle mold manufacturers, and they're able to take on the complex work that they normally would turn down. So with scanning, the complexity isn't really the issue. There are different sets of issues when it comes to recreating, digitized files that are in the physical world, but a lot of the complexity problem goes away. So they were able to take on some jobs that obviously you can charge a little bit more for that are very complex and detailed. And the lead time was greatly reduced. I think the number they threw out was 40 hours or more before, and they cut that in less than half from start to finish, between the scan, the toolpath creation, and sending the mold out to the customer for approval. So quite a good application there. Another one is aftermarket products. So this is a sort of die-cast housing, and you can see on the left there that is a very, looks like parametric-based file, but it could have been reverse engineered from a scan that they did. It may have not had access to that CAD file. So if it's a third-party product and they didn't create the drawings or the 3D, they're probably not going to get that information. But if they still have an idea for a product to make it better, they may want to manufacture this housing cover to fit. So you can see the item in red was really based off of the mating surface and features of that die-cast housing in blue. So it doesn't always have to be the end-use part directly that you are creating. It's sometimes the mating parts, or it's an improvement to an existing part. I've been a part of some projects such as creating water filters for your refrigerator, and capturing the mating detail that's required, but instead of using company A's filter size filter cartridge, they wanted to use company B's that had a smaller filter. So the whole housing was a smaller footprint, but the mating detail was needed so that it would still fit into the refrigerator, for instance. So different applications for aftermarket product development and improvement. This is an interesting one from CIRAS, our MEP friends in Iowa. So they had a customer, Danfoss, that was having a constant breakage issue on one of the fans in the machines that they were running in production. So they didn't have the data on the fans, but they were able to capture it using 3D scanning, and they were controlling the data. So if you control the data, you control the manufacturing, right? That's the information that's needed to produce that entity, whether you're doing it yourselves or you're farming it out to a supply chain. And the parts with the longest lead time and the excessive relative costs, we've all been seeing, like, why does this little motor cost $150 when there's $2 worth of material in it? Well, that's just a series of middlemen basically being in the supply chain, right? So controlling that and taking some of those items that seem really out of whack with reality can be a great, not only cost savings, but potentially lead time savings and keep production going. So that's what they were after here. So they controlled the data, they controlled their own manufacturing uptime, basically. This was the critical fail point. And then another one is legacy part digitization. This is one from the Netherlands from a few years back, but you know, a lot of these old, especially you see this all the time in defense. You know, they've got old aircraft, they've got old boats that they are trying to, old ships that they're trying to keep alive in service, but they've got parts on them that are decades old. You know, made last century, and it's like nobody has the data. 3D barely exists back then, so how do you recreate these parts? So scanning is a great tool. This is probably the area you read about the most outside of metrology when it comes to legacy part digitization through scanning. So again, they control the data, they control the manufacturing, whether it's, you know, internally milled or printed or sent out to the network of you know, manufacturing partners. And ideally, might be able to redesign it. So if it hasn't been looked at in 50 years, potentially you could make it simpler and make it more manufacturable using some new technology, such as additive or 5-axis milling, and avoid tooling, you know, avoid having to tool up for especially a small number of parts. So not just the data capture part, it's doing something with it. You know, can you make it, can you build on that? And does the application allow for an improvement at that point to bring it into this century? So these are just some suggestions when it comes to legacy parts. Collector cars are another great avenue. I've done this personally in the past. Again, price point is not always the top of mind. It's just about fitting it and getting the look consistent. So yeah, producing a one-off part is sometimes very expensive, but in the end, the customer gets the exact fit, the exact look, the exact vintage that they want for their automobile. So just wrapping this up, you know, 3D scanning is that digitization of, you know, the physical object that you have when you don't have the CAD file available for it, or a 2D drawing that could potentially be reverse engineered using the drawing into a 3D file. It's really a must-have going forward with advanced manufacturing. Everything is based on 3D for the most part. And then the hierarchy. So I mentioned the file types earlier. So surface mesh, that's kind of with the starting point. That's going to be what you can do the least with, but it's the simplest as far as once I'm done painting the part with the scanner, I'm basically optimizing that and doing some repair, hopefully very little, and then I've got the surface mesh. From there, I'm doing a full surface repair, going through, analyzing any facets, any non-manifold edges, anything like that, open edges basically that need to be patched and repaired. Maybe even go back a step and by, you know, digitally go in and draw all those gaps. But hopefully a wizard or some sort of repair tool can do that. The dumb saw is then based off of that non-manifold surface file, which you can create a 3D for. So non-manifold surface is basically the skin, and there's nothing behind it, right? And then now we want the whole 3D object. So the way to do that is to create that dumb solid that doesn't have any features, which you can go back and recognize and edit later. And lastly is that full-blown feature-based solid that takes the most engineering time and takes a skill set and some training on. Even if you've done CAD before, for example, if I've done SolidWorks, but I had to go through at least an initial training to be somewhat well-versed in doing a reverse engineering product for full 3D solid file creation. So the first 2, maybe 3 steps you can get by without doing much training on the reverse engineering side, but the 4th step of the fully smart solid, I'll call it, probably needs some training. We were talking about some of the other applications. Think about those in your facility. If any of those might apply, or if you maybe want some assistance in identifying applications, let us know. Happy to do that. Build the case for you. Sometimes it's hard to justify buying a scanner, right? If you only, you're gonna need it once, but you may not need it, you know, in the future. So a lot of times it does make sense to use a third-party service, but you know, if you've got several ideas, and I recommend starting with a third-party and then coming back and maybe identifying building a business case for ownership of one outright. And then just pricing, we didn't really talk about that too much, but really they're based primarily on your needs in the way of speed, in the way of the accuracy that it can achieve, and then, you know, the range, the field of vision, whether it's on a multi-axis arm, or if it's a, you know, like a photogrammetry. We didn't talk about that, but taking large format photos of, you know, buildings, bridges. You know, there's all sorts of technology, and they're priced accordingly. So with that, I just want to touch on a couple other things. Connexus, Indiana, hopefully you guys have all seen this announcement, but they recently renewed the Manufacturing Readiness Grant that will be in place for 2021 and 2022. And we at MEP are helping assist clients with the application and giving you tips on how to present the best case for your technology. So this is not just buying a better CNC machine now. This is Industry 4.0 related technologies. And we can give you some examples and give you some specific awardee information from the past to give you an idea of what has been approved and what has not. So if you have any questions about this, let us know. This is a great opportunity. These don't come along that often when we talk about potential grant matching funds for equipment. We do a lot with training, but when it comes to capital equipment, this is one of the few in Indiana. So take advantage of this if you're looking at any of these Industry 4.0 types of technologies. And then just a quick snapshot, what we've got going on at Purdue MEP the rest of this month and next month. I guess July, or basically July tomorrow. So we've got some Six Sigma, some cyber. So we've got free webinars like today. We have 4-fee workshops and then 4-fee on-site training for your company. So if you have a topic you're interested in, whether it's on here or not, check out our website and let us know if you have an interest, and we will see about either putting a workshop or on-site training together for you. Appreciate it. The time today. Again, if you have any questions, comments, please email me at kvschool@purdue.edu. I think we've got time for a few questions. Laura, do you have any questions in the chat or the Q&A?
I do have one question that came up. What are the dot stickers used for that I'm seeing in the scanning video?
Yeah, I don't know if anybody caught on to that, but either the object or the turntable that the object was sitting on had some dots that were black ring with a white circle, white inner circle. They're a 1/4 inch to 1/8 of an inch usually. These are largely used for accuracy improvement. So by placing these dots on the turntable, you can even move the part around if you need to. If the turntable obviously spins, but if you're on a surface without a turntable, you can put dots on a table that's fixed and move the part and have the part register because the dots are on the table and the orientation can be matched up. So largely used for accuracy and alignment purposes. For small parts, again, it's best to put it on the surface that the part is resting on rather than the part itself, because the dots take away that feature on the surface that's being scanned. So yeah, those are an improvement. They're not always required, but especially for the structured light scanners, a lot of times those are a requirement. Anything else? Looks like we've got a couple in the chat. I'll go ahead and take those. Is there any decent open source 3D scanning hardware or software that we can use? Decent, yeah, it kind of depends on your definition of decent. So I've used a small turntable in the past. It was sort of open source. It was not good. This was probably 6-7 years ago though. I know it's gotten a lot better, and I'm not too privy to some of the open source 3D scanning as much as I am on the 3D printing open source. So I will say this, that I mentioned photogrammetry, which is using photographs instead of light reflection. Photogrammetry is really taking shape in our phones. So like Apple just announced they're putting in, I believe it's the capability to do 3D scanning in like some of the newest phones that have come out this year. So built in, so with a likely a purchased app, you could use your phone to get a decent scan of something. Now, it's not going to be metrology grade, and a lot of times they say, you know, 1% or so accuracy, and a lot of times that's not nearly good enough for manufacturing. So it depends on what you're doing. Artistic things, you know, packaging potentially, there's more clearance around parts. Yeah, the potential is there for like for a tablet with a really good camera in it to be used as a scanner. The software, you know, I can follow up with you and send you a list of things that I've found, but I'm sure there are some out there. It's just not quite as, not at least known to me as far as compared to like another question we've got, you know, Microsoft Connect, Blender. Okay, yeah, as far as the software. Yeah, again, I'm not familiar with either of those too much. Blender we use a lot with additive, with 3D printing. And then good tools to take point clouds to STL files. Point cloud data to STL. So the one that I'm using is tied to the scanner. So VX is a Creaforms package. DesignX is owned by 3D Systems. They both have really nice packages. NetFab, I believe NetFab is one that is more independent. And while they may be owned by a large company, but they have a, it's not necessarily tied to a scanner. So you can essentially use NetFab, import a mesh file, and do the editing and fixing and take it all the way to a 3D solid. So NetFab is one that I'm aware of that does a good job. Blender, I believe, does a little bit of that, but I don't think it does full 3D solid feature-based 3D solid. Again, I can look into that for you if you like. Jamie, good question. All right. Well, thanks, everybody. Appreciate your attendance, and let us know if we can help in any way, whether it's technology related or not. We are here to help manufacturers. So thank you, and we'll see you next time.